I'm going to give it 60 more seconds. All right, let's do it. Homework. What is this? Homework 5. Homework 5. Okay. An auditorium has dimensions of 22 meters by 20 meters by 8 with 18-meter ceilings. Each surface is made of the same material, and the reverberation time for a frequency of 250 hertz is 2.5 seconds. Calculate the Sabin absorptivity of the empty room at 250 hertz. This is another one of those high school physics kind of problems. We've got an equation. We've got some quantities that we know. We got a quantity that we don't know, and we're just going to solve for the one that we need. So that equation's right there. T60 is your reverberation time. You've got that constant 0.161. You got volume. You've got surface area, and then you've got a Sabin absorptivity, which is that A bar thing right there. So we're just looking for that A bar thing, and we should know everything else, or at least be able to calculate it, right? There's not too much to that one. Any questions there? You guys feel okay on that? Yeah. Yeah. There's not, you know, if you run into something, if something's not clear, always email me. But I think that's pretty clear. So now we've got to determine the reverberation time at 250 hertz when upholstered seats are installed in the concert hall. Assume they occupy 70% of the surface area of the floor, and that the volume of the room doesn't change. Okay, so we've got a new equation here, though it's just kind of a version of the other one. And this is another one that was presented in class. So we've got this T60 prime here, which is our new reverberation time. Our volume hasn't changed at all. We've got S, which is this total surface area, which is the same as it was above. But now we've got S1, which is the surface area being covered in new material. So what you need to do is you need to find the surface area of the floor, which is pretty easy, and multiply that by 0.7, right? And that's going to get you that S1 number, right? Multiply that by your original Sabin absorptivity, A0, subtract that out, and then just add the new one in. And that new A1, that Sabin absorptivity of the seats, with the upholstered seats, right? That's just in that table at the bottom of your homework. You can find that. It's in the second table. I think there's 2. Yeah. So plug that in, run it through. Bob's your uncle. You're good. Okay. Okay. So this one takes just a bit more thinking, but not that much more. If every seat is filled, how many acoustic tiles with a total surface area of 2 meters squared need to be suspended from the ceiling for the reverberation time of the concert hall to be less than 1.9 seconds? Assume that the volume of the concert hall remains the same, no matter how many people or acoustic tiles are inside. Note that the tiles are suspended from the ceiling, so they add additional surface area. They do not replace any surface area of the walls. You don't need any new equations here. We have everything we need. Okay.
So does this mean like kind of thing is beyond it?
Yeah, so they're suspended from the ceilings. I think if I'm picturing it, you know how, have you been in a concert hall where they're like, there's acoustic tiles and they're parallel to the surface of the ceiling, but they're hanging from each corner by like a cable? I think that's what we're talking about. But the point is the volume is going to stay the same. That hasn't changed at all. The surface area, the total surface area has become larger. So we're going to have this new component in there. Yeah, they're not covering the ceiling. We're in this version of this problem, the sound waves can completely get around them and interact with the ceiling the same way they did before.
So this mean like should work for like both sides of the thing?
we're not going to treat it that way, but that's a good question. Yeah, you're right. It would, right? Because it's going to reflect off the ceiling and be absorbed by the back of the ceiling tiles. But let's pretend it's not. I think is what we need to do here. And I have confirmed that because I know what the answer is, and I know you don't do that. But that's a really good question because that's how it would work, right? Yeah, that would be a factor. Good question. Okay, so we've got this thing here. This is the same equation we had for the one above it. And the move here is we're going to rerun this. We know T60 prime now, or T60 double prime, whatever we want to call that, our new reverberation time. We're going to run this thing. We're going to kind of forget that we did part B at all. Come up here to part A and use our new Sabin absorptivity for filled seats. All right, that makes sense. That's the first part of it, right? But then there's another term. So that gets us as far as what would be the reverberation time if we had filled seats instead of empty seats. But we need to know how many tiles we need to add in order to get the reverberation time we're after, which is 1.9 seconds. So we need to add a new term. And that new term is going to look like something like this in the denominator. Oop, let me talk to it. Uh-oh. Uh-oh. I just charged it, so. And do that? No. Okay. Sorry, guys. So can I do this with my finger if I wanted to? No, you can't. Anybody know any tricks for connecting them if they're not connected? Sorry, 1 second. Oh boy, I don't want to do that. Oh, like try like that? Yeah, let me try. Thank you. And we'll know about it. Oh, you're a genius. You get 100 on this homework no matter what. Okay, here we go. Now we're cooking with gas. So let's add a term at the bottom here. And this term is going to look like a surface area times Sabin absorptivity, right? That Sabin absorptivity we can just get from the table. That's easy, right? Let's just call that A2, right? Here. But we need to multiply that by the surface area. And we've got this thing that we don't know, which is how many of these tiles we have. We know that each tile is 2 meters square, right? So it's just let's call this X or whatever you want, right? And that's what you're solving for. You can do that by hand. You can plug it into MATLAB. You could put it into Desmos, whatever you want. I don't like that X there. Let's call it something else. Let's call that N. Yeah. That seem right to you guys? Seem reasonable? Right? Just make sure you keep your surface areas and your absorptivities straight, like which one's which. So again, you're going to forget that you did part B at all. That work is unnecessary because we've changed our absorptivity, right? So you're starting from A again and then using this equation. Does that all seem okay? Pretty good? Okay, sweet. We're going to talk a little bit about part 2 and then a little bit about part 3, but we're not going to do all of either of them. Part 2, you are measuring the response of a room that has dimensions LX, LY, LZ, and they are 5, 4, and 3 meters respectively. During your measurements, you measure a large resonance at a frequency of 57.17 hertz and are assigned to build a bass trap to compensate for this. Your design will look similar to the one shown below. To choose a location for the bass trap, it is necessary to figure out which mode of the room is problematic. for a room of these dimensions, which normal mode has a frequency closest to the observed value. So here's your equation, right? You're gonna have to run a few of these and figure out which one it is, right? This is a trial and error type of deal. So I guess, I don't know, you could probably be fancy and plug it in for F and then solve, but I don't think that's the smart way to do it. It'll take you longer to figure out how to make that work than it will be just to run a few of them until you get the right one. I did it in MATLAB and made a little matrix with them. I can tell you, you don't need to go to like, you know, the 175/30 mode. It's not that one. We're talking, let me tell you that it's somewhere less than 3, right? You don't have to go that high. Do it in a matrix, do it by hand, do it in Desmos, and then just change your L, M, and N systematically until you get what you're looking for, right? Easy enough. You guys okay with that? Everybody cool? Got an equation, got a way to do it. Okay, part B. You decide that the best way to compensate for this mode is to build a bass trap along one wall of the room. What is the surface area of the wall you will choose? Explain why you chose this wall. Hint, there is more than one wall that would work. So the reason he's asking for the surface area is he wants you to tell him which dimensions. Is it the, we're talking about the floor or the ceiling or whatever. It's just a way to say which one it is without getting confused about whether it's a wall or a ceiling and which one or whatever, if that makes any sense, right? But really what we want to know is, you know, what are the two side dimensions? Is it the XY wall or the XZ wall, or which one is it, right? Okay. Okay, so I don't think we talked about this in class, and I'm curious what you guys think, and I want to talk this through a little bit. So let's start here. Let's go back to strings for a second. So I've got this string, right? And this is the n equals 2 mode of this string, right? Single sine wave, yeah? You with me? If I want to stop this thing from vibrating, right? It's been excited, and this is the mode, and I want to stop it, right? Physically somehow. Where am I going to place my damper, my finger, whatever I'm using to stop this thing? Where do you want to put it at to take energy out of this thing most efficiently? What if I pinched right here? Is that going to do anything? No, right? Doesn't matter, right? If I try to stop this thing on a node, right, it's not going to interfere with its, you know, motion at all, right? So where do I want to try to pull energy out of this thing? Same place I'd put energy in if I was trying to do it. Sorry, what'd you say? Internet?
The antinode?
Yeah, the antinode, right? Here or here, right? Okay, bearing that in mind, let's think about this in terms of, so we know we want to be on an antinode. We know that much so far, as far as where we want to place this absorber, right? Let's find out where those antinodes are in this room. Well, we actually already know. Where do antinodes show up in a room? What's the fundamental difference between this shape and the shape of a wave in a room mode? Let's just draw one dimension here, 2 walls. Doesn't look like that. Looks different. How so?
For scanning, it's fixed, but you're kind of like dealing with the empty space defined by the walls, not like including the walls itself.
Yeah. So what, this is a sine wave, right? That's not true for a room mode, right? It's what? It's not a tangent. What's the other one? It's a cosine, right? So it has, let's do, I'm gonna do better on drawing this. So I'm gonna do like You're like this, right? That's a half cosine. That's n equals 1, right? I know I drew n equals 2 up there, but this is my n equals 1, which is just the simplest case. So I know my antinodes are at the walls, right? So that's sort of put in the question that we want to do it somewhere. We're putting it on a wall, but there's the y, right? Antinodes are at the walls, right? Because it's a cosine that has to fit in there, not a sine. Okay, so we know we're putting it at a wall, but which wall? I want to, this is it was hard for me to kind of figure out a way to illustrate this, but I think the best way might be to run that program we looked at in class. So I'm going to pull that up for a second and stop sharing my iPad. So let's see if this will run. Yeah, that'll work. Right. The internet, are you guys able to see that picture?
Yes.
Okay, cool. So in this scenario, we have one, it's like, let's see, I think it's the x dimension, z dimension. Sorry. No, sorry, it's the y dimension. The y, it's 0, 1, 0 is what I'm saying, right? So it's the y dimension where there's actually a wave, right? There's not a wave in x or z, right? And that's that plane of constant pressure, this green thing here. So if I flip it this way and we look in y, we can see that go from 1 to 0. It's a half cosine. I know that's sort of hard to picture, but from left to right, it's going from 1 to 0 because that's the y-axis. Looking at this cube here, right? There are 2 walls where I have pressure maxima, right? They are the places where it makes sense to put those absorbers, those base traps, right? It doesn't make any sense to put one right here. There's no maxima there, right? I don't know how well you guys can see my mouse, but right there at the front doesn't make any sense, right? The top doesn't make any sense. There's no maxima there. The far side, the one you can see the least, doesn't make any sense. The bottom side doesn't make any sense, right? Because there's no waves that have those antinodes on those planes, right? There are 2 where it does make sense. This kind of front face, this right here, right? Because it's a minima, but it doesn't matter, right? It's, minima or maxima, it's fine, right? Or this side, right? So that's those are the walls where you would put this. And what you need to do is just translate what you find as far as like what the mode is into what I'm saying here, right? So to just break this down just a little bit further, this wave is in the x-axis, right? So the YZ plane didn't make any sense. I guess there's 2 of those. Well, scratch that for a second. Like I said, it's a little bit tough to visualize this, but you might consider running this on your own when you figure it out, to try to make sense of where that is. And we're also, I think, going to talk about this in class, and hopefully it'll be clear at that point as well. But that's kind of the idea. I hope that helps a little bit. Let's look at one last question here. So let me reshare. One last one. Yeah, one last one. We're going to skip C because we haven't talked about that in class. On number 3, we are going to skip A and B and jump right to C. So this is this question about T30s and T60s. It says if the T30 for a room is measured to be 1.5 seconds, which of the following times would you expect to be closest to the T60 value? Explain your reasoning. So the question is, how do T30 and T60 values relate? Should they be close to each other, far off from each other? What's the relationship between T60 and T30? T60 is what? Not quite. Good though. So T60 uses twice the amount of data, twice the time to make the estimation, but it shouldn't be double.
It depends on the noise floor.
Depends on the noise floor. So that's right. It depends on the noise floor in terms of whether you should use it. T30 you use if it's too noisy to use T60. If I have 60 dB of dynamic range, right? If the noise in the room is low enough to where I can excite it with something 60 dB above the noise, then I can use T60 and I'm fine. I don't have to think about T30. What T30 is for is, say, it's noisy like it is in this room, actually, right? In order to excite this room 60 dB above the noise, I'm going to need some special equipment and I might damage my hearing, right? Does that make sense, right? But I can probably excite this room with an impulse that is 30 dB above the noise floor in here, right? That's going to give me a T30 value. But at the outcome, at the end, how do they end up being different? Anybody in the internet want to venture a guess? Do you expect them to be close to each other or not close to each other? Close, right? In fact, all things working out perfectly, they should be identical, right? So T30 is an estimate for T60, right? That's all it is. The value should be the same, right? You're just extrapolating that extra 30 dB, right? So you only need 30 dB to sort of establish a slope. You establish the slope over 30 dB, but then you just follow that slope all the way down to what it would be if you had 60 dB to work with. That makes sense? Feel okay about that? Kinda? Okay. Let me see if I can draw something that'll make it more clear. Okay, so let's say this is -60 and here's 0. And I have something in decibels that looks like this, and this is time, okay? I have a T60 value here, right? You okay with that? I've excited it, at 0 dB relative to that -60. It's, dropping off. It's exponential, but I put it in decibels, right? So it became linear. And I have a time for T60, right? But let's say my noise floor is here. Here's my noise, -40. Well, I'm not going to know, right? I'm not going to know when it drops by 60 dB because I can't see it. Because the output is going to get stuck at -40 because even though my impulse has dropped off below, right, the noise has taken over, right? So I can't make that measurement. Now I could always push up the excitation, but there's limits to that, right? If I could excite this at +20, I would be fine. But let's say I couldn't, right? Or it wasn't practical for whatever reason. Or let's say the noise floor was higher. Does it make sense why you couldn't always take a T60 in a noisy room? Okay, cool. So what I do is, here's -30. right? I find this value right here in time, and I double it. You see what I'm saying? Right? My T30 still ends up being my T60 or close to it, but it's an estimation, right? And if that slope changed, if it was like this, right? Well, then my value is going to be wrong by some amount, right? So the T30 is just an estimation of T60. And the reason that you need it is because you can't always make an excitation that's 60 dB above your noise floor. Does that feel any clearer? Yeah, okay. The long and short of it is those values should be the same or close to. They won't be identical, otherwise there'd be no need for a T60, but they should be close. Okay. I think that gets us through everything. Any questions about anything on this homework or otherwise? Okay. Record time today. When's the homework due? The 12th. Okay, yeah. I figured we'd have another one before it was due. Yeah, so we'll talk about the rest at that point. Cool. All right, email me, you got questions. Have a good day, everybody.
Thank you.
Yeah, no sweat.